Welcome to the Test 3B review, our video review over complex numbers. What you need to make sure you have are any notes that can help you, a calculator if you use one, your computer to view Desmos, and a pencil and paper for obvious reasons. All right, here we go. Go ahead and pause the screen if you need more time writing down the first 3 problems. And here are the last 2 problems. After you write down the problems, you can skip ahead to the part of the video that you need, whether it just be the quick solutions section to check your work quickly, or if you need to go through any explained part of any problem, you can zoom ahead to that. Good luck. Here in number 1, let's take a look at defining each one of these mathematically. In part A, I is the imaginary unit. Mathematically, it's the square root of -1. Part B, I squared, is taking what I equals and squaring it, and so it's the real number -1. And C, a complex number mathematically, is A plus BI, where A is the real part, and BI is the imaginary part. So a complex number includes all imaginary numbers, and a complex number is a number that is comprised of both a real number and an imaginary number, called the real and imaginary parts, A plus BI. Simplifying radicals when there are negatives under the radical gives us the possibility of bringing I into the situation. For part A, we do not have an imaginary number. This is simply 3. Now it's positive 3 because we don't have a negative sign in front of the radical or a plus or minus sign in front. We only want the positive answer. Part B, the square root of -9, if we want to see how that breaks down, we can break that down into the square root of 9 times the square root of -1. The square root of 9 is 3, and the square root of -1 by definition is I. Therefore, the square root of -9 is 3I. Part C, there are a few ways to do this one, but what I'm going to do is just do it step by step and break down the square root of 9 and the square root of 16. The square root of 9 is just 3, square root of 16 is 4, and multiplying those we will get 12. Part D, we have negatives under each root. Therefore, when we break this down, the situation's similar to part B here, so we already know that the square root of -9 is 3I because of what we did in part B. Similarly, the square root of -16 is 4I in the same way. When we multiply 3I times 4I, we'll get 12I squared. I squared equals -1, and therefore, when we multiply, we'll get -12 as our final answer. So that's the difference between part C and part D. In part E, since we have both of the numbers being multiplied under the same radical, we need to first multiply them together. And when we multiply that negative times a negative, we end up with a positive 144. So that is what we have under the square root. The square root of the positive square root of 144 is positive 12. Here we have 2 complex numbers. I'm going to go through each one of these fairly quickly. A and B are not too bad. They're just adding and subtracting. So we're going to add these 2 together, 5 minus I plus 4 plus 3I. Note that when we're adding, we do not need any parentheses around the complex numbers because adding is simply combining like terms. And we'll be left with 9 plus 2I. In part B, we want to subtract V minus W. When subtracting, we do need to care about the order that we're subtracting. And I do need to put parentheses around what I'm subtracting since we will have to distribute that negative sign through. When we distribute the negative sign through, we'll have -4 and -3I. Then once again, we combine our like terms. Our real part will be 1, and our imaginary part will be -4I. When we multiply, we want to make sure that we end up with 4 terms here because we have a binomial times another binomial. So I'm going to first distribute the 5 through, so we'll get 20 plus 15i. Then we want to distribute the negative 1i through, and we'll get a minus 4i and a minus 3i squared. So we can combine our like terms with I, and that will give us plus 11i in the middle. Then I'll replace I squared with what it equals, which is negative 1. So this turns this final term into a plus 3. So we actually have 2 real numbers here that we can combine to give us 23 plus 11i. To square w means to multiply it by itself, and so this is essentially the same exact type of problem that we just did in part C. Multiplying w by itself means again distributing both terms through, so we'll first distribute the 4 to get 16 plus 12i. Then again, we'll distribute the 3i through, and we'll get another 12i, and then plus a 9i squared. We'll combine these like terms in here to get, oops, I didn't write 12 before, to get 24i. Then we will replace the I squared with the negative 1 that it equals. So that's a minus 9 over here. So we end up having a 16 plus a 24i minus 9. Combining our like real terms here, we'll get 16 minus 9, which is 7 as our real part, and 24i as our imaginary part. In order to divide in part E, we need to multiply both the numerator and the denominator by the conjugate of the denominator. The conjugate of 5 minus I is 5 plus I. So that's what we'll multiply the numerator and denominator by. 1 times that is just itself, 5 plus I. In the denominator, we are multiplying a complex number by its conjugate. When you multiply a complex number by its conjugate, and you don't really end up with 4 terms because the middle 2 terms will cancel out. Because of this, you only need to multiply the first by the first and the last by the last. You could end up multiplying all 4 to get 4 terms, but again, the middle 2 will cancel out. So instead, we can just take the shortcut. We'll be left with 25 minus I squared. Of course, I squared equals negative 1. Since I squared equals negative 1, we're subtracting negative 1, which means adding. So our denominator ends up being 26, and our numerator is 5 plus I. To write in a plus bi form, we want to first see if we can simplify it all, which we cannot. Our real part is 5/26, and our imaginary part is 1/26i. In part F, in order to divide, we need to multiply the numerator and the denominator by the complex conjugate of the denominator, which is 4 minus 3i. When we multiply in our numerator, we do need to end up getting 4 terms, so we'll distribute the 5 through to get 20 minus 15i, so I multiplied here. Then we'll distribute the I through to get plus 4i, and then minus 3i squared. In the denominator, because we're multiplying a complex number by its conjugate, we only need to multiply the first by the first and the last by the last. So we'll get 16 minus 9i squared. Again, that's a shortcut. Now we want to simplify. I'm going to simplify over here. In our numerator, we'll have a 20. Then combining like terms, a minus 11i. Because I squared equals negative 1, this term turns into a plus 3. And in our denominator, the same thing. This term turns into a plus 9. So 16 plus 9 is 25. The numerator can be simplified to 23 minus 11i over 25. We can't simplify any further by canceling. And so in order to write an a plus bi form, our real part is 23/25. Our imaginary part is minus 11/25 I. Number 4 is pretty simple. A complex conjugate rather, means the same real part but the opposite imaginary part. So for part A, this complex number is really 0 plus 2i, therefore its conjugate would be 0 minus 2i, or just negative 2i. In part B, the complex number is 5 minus I, therefore its complex conjugate would be 5 plus I, changing just that inside plus or minus to the opposite. In number 5, we see that we have a cubic function, and I've graphed it on Desmos. Using Cauchy's bound, I'm seeing that even if we zoom out to the negative 26 to positive 26, we only cross the x-axis one time. Therefore, we only have one real root, multiplicity 1. That root is negative 1. And that means that we have two complex roots, which we need to find using the quadratic formula. So let's get through that process first. So this means that since negative 1 is a root, when we perform synthetic division using negative 1, what we will do is divide by x plus 1. That's essentially what we're doing. And then we'll be left with the quadratic from dividing by x plus 1, the factor that goes with negative 1 being the root. So when we perform synthetic division with negative 1, we'll be left with the quadratic that we can then continue to find the last two complex roots for. So we'll bring down our 1, multiply, combine, multiply to get 8. 17 and 8 is 25, and then multiplying, we will end up getting that 0 there that we knew we would get. The quadratic that we end up with is x squared minus 8x plus 25. So that's our quadratic. We know that the two roots are complex, therefore we're going to use the quadratic formula to find them. So we'll have that a is 1, b is negative 8, and c is 25. Using the quadratic formula, we have the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Simplifying the discriminant, which is under the root, we're left with 64 minus 100. 64 minus 100 is negative 36. The square root of negative 36 is 6i. Then we can simplify all of this. Since we can simplify all three terms, we'll divide them all by 2 and end up with 4 plus or minus 3i all over 1. We don't need to write the over 1. 4 plus 3i and 4 minus 3i are our final two roots. Therefore, our three roots are x equals negative 1. That's our real root we got from the graph. Then the complex roots are 4 plus 3i and 4 minus 3i that we got through synthetic division to get down to a quadratic, and then using the quadratic formula to solve the quadratic.